So when we're writing an exponential in logarithmic form or a logarithm in exponential form, we're going back to the notes that we took down yesterday. And everything's going to just rely on where the various parts are in this setup. So for instance, in this case, I'm starting with the exponential. So that means I'm writing as a log. So first thing I write down is log. In writing my log, you notice the first thing after log is b. The value of b is the number that's being raised to a power in the exponential. So the number that's being raised to a power here is the 6. So that means my base is 6. Remember, when you write the base, write it smaller and lower. It's a subscript. Next up, when I write my logarithm, comes the y value. Y is what the exponential is set equal to. So in this case, the exponential is set equal to 36. So it's log base 6 of 36. Equals, and again we can see what that is. It's the x value, which is the exponent from the exponential. So in this case, that's going to be a 2. So we get log base 6 of 36 equals 2. One way to help yourself remember these, log always equals the exponent. And so that already is something you can get in right away at the start. All right, now on to number 2. We're doing the exact same thing, just this time instead of 6, 2, and 36, it's r, t, and a. So first thing I write down is log. The base is the number that's raised to a power, that is r in this case. The number that next goes is what the exponential equals, which is a. And log always equals the exponent, so it equals t. So there we get log base r of a equals t. Repeat the same process with number 3. I write my log. And then the first thing I write down there is whatever's being raised to the power. In this case, that's a 2. Yes, it's on the right side here and not the left side, but it still works the same way. It's still, the base is just whatever is raised to the power. I know it's going to equal the exponent, so therefore it has to be log base 2 of 1,000 equals x. For 4, 5, and 6, we're doing the exact same thing, but in reverse. So for instance, if I take a look back at my notes, the first thing I'm going to write in my exponential there is the b, which remember is the base of my logarithm, the small number. So in this case, in number 4, that's going to be the 3. The exponent on the 3, that's the x value from our notes. It's what log equals. So whatever is by itself on the other side of the equal sign, that's the exponent. So in this case, that's the 4. So we got 3 to the 4th equals, well, it's got to be the 81, doesn't it? So number 4, 3 to the 4th equals 81. Number 5, same thing, just with letters, not numbers this time. The base is t. Log equals r, so that's going to be my exponent. So t to the r must equal p. And finally, for number 6, the base is 3. That's raised to the power of whatever log is equal to. Again, it switched sides this time, but it's still the same idea. I'm looking to see what's by itself to know what the exponent is. So 3 to the w equals 21. Make sure you have each of those down correctly. So the next up, we're now going to be looking to see how do we actually calculate these values. So you're going to need your calculator for this. Yes, your calculator must have a button on it that says log. All right, so the first thing we're going to do is we're actually going to calculate the value of log 30. Now this is just a fairly simple matter in the calculator. Now depending on what type of calculator it is, you'll either press log 30 or you'll press 30 log. Generally speaking, the way to know which way, if you press the log button and your calculator actually displays the word log on its screen, that means it's doing it as you type it in. It's doing it literally. So if yours is that way, you're going to type in log, then press 30, then press enter. Now if it doesn't show that way, means you're probably using a scientific calculator. On a scientific calculator, you would type in 30 and then press the log button. If you do it correctly, you should be getting an answer of 1.48. So make sure you can get the correct answer out of here before we go on to the next part. All right, so having gotten number 1 down, that means you at least got the keystrokes down, you got the idea of how to use a calculator for finding log. But for number 2, it's actually a different kind of beast. Because most calculators do not have a way for you to enter a different base like we see in number 2. So because of that, there's actually a special formula. And you're going to need to know this even if your calculator does do other bases. This is the change of base formula, and it's going to need to go into your notes right now. So go ahead and write this down, and then we're going to see how it applies. And as you get this down to your notes, you notice that little double-headed arrow there? That just means that these two statements are equivalent. So it's meaning that we can write the same thing either way. Now, some little details here. You notice the original is log base b of y. When I write it over here, it's log y over log b. There's no bases written in on either of those two logs. That's because we're just going to use the plain old log button on your calculator. So you don't have to worry about a different base. It's called change of base formula because it allows us to calculate what the logarithm is with a different base when our calculator doesn't do that. Alright, so you have this down to your notes. Now let's go see how to apply it. So on number 2 there, we're doing log base 5 of 20. In order to calculate that value, we use change of base formula, and I write it as log 20 divided by log 5. So start by writing that down in your work, and then do that calculation. When you do this calculation, again, it depends on what kind of calculator you're using. If it's on a graphing type calculator where it's showing you what you type in, you do log 20, end the parentheses, and then divide by log 5. If you're doing it on a scientific calculator, you do 20 log, divide by 5 log. Now when you press 5 and then log, the number that's displaying is the log of 5. So you still have to then press enter to tell it to do the division. So again, on a scientific, that means 20 log divided by 5 log equals. If all goes well, you should be getting an answer of about 1.86. So make sure that you're able to get the right answer there before we move on to the next step. Alright, so now on to number 3. The first thing we do is we rewrite it using change of base formula. So first up we get log 3 divided by log 15. Now something to make note of here. Sometimes people say, oh well, the number that's the bigger number goes on top or bottom. But notice it doesn't. The base is always the number that goes on the bottom, regardless of whether it's bigger or smaller. When you do log 3 divided by log 15, you should get about 0.41. Side note here, you'll notice I'm rounding all my answers to 2 decimal places. That's just because we were told in the instructions here to round to the hundreds.
I got 0.4.
Alright, then for number 4, we do the same kind of thing. We set it up as log 8 divided by log 16, and that gives us exactly 0.75 in this particular case. And then finally for number 5, that one also ends up working out very nicely. We end up getting 2.5 there if our calculations have gone correctly. Make sure you can get each of these calculations out so that you're going to be able to do these correctly in the future, because changing exponentials into logarithms is step 1. Step 2 is calculating the logarithms. Then we're going to actually be able to use these to solve equations. All right, now we did these calculations using the log button on the calculator, just like we did in number 1. But when we did number 1, what was the base there? Because there was no base written in. And like many things in math, it's like there's this assumed number if we don't write it in. So like for instance, if I just write x, well that's really 1x, right? Yep. Or if I write root x, well that's just the second root of x, but I don't have to write the 2 in. If we don't write the 2 in, we assume it's square root. Logs have the same thing. If we do not write the base of a logarithm in, it's assumed to be a 10. So this should also then go into your notes. Log x is equivalent to log base 10 of x. You don't have to write the text down below it if you don't want to, but it can be a nice clarification if you want to include it as well. So now next up we're switching from taking a look at some of our logarithm work to some of the work that we were doing yesterday dealing with graphs. Yesterday we made graphs from equations. Today I'm going to start you off by having you tell me what the equation is based on the graph. Now you don't have to copy this whole graph down to your paper. Focus just right now on what the graph looks like and how you would write the equation for it. Now when writing the equations from the graphs like these, step 1, you don't need to worry so much about the curve as you do about the points. Focus on where those points are that are making up that curve, because they really tell us the story. So take a moment, look at this graph, look at those points, see if you can figure out what the equation is, and then we'll go through it here in just a moment. All right, now a few things that I hope are leaping out to you as you take a look at it. First of all, you'll notice we got the asymptote drawn in there. The asymptote is at 2, which means that we know that at the end of our equation here we're going to have a plus 2. And since this has an asymptote, it's leveling off on the left side, it's getting really steep on the right side, we know it's going to be an exponential as well. So that tells me it's going to be something to the power of x. And that's what y is going to equal. The question then is, what is raised to the power of x here? Well, our first point's up 1. That's good. That's where it normally defaults to. But then after we go up 1, we go up 2, we go up 4, we go up 8. What are we multiplying by each time? 2. So it's 2 to the x. So that's our basic strategy, is we want to see how much is my height being multiplied each time we go over. So let's practice that idea with this graph. So again, take a moment, look over it first, and then we'll take a look at together to write that equation out. Right, so writing this equation, of course the shape already tells us that it's going to be something to the power of x. Okay, the question is, what to the power of x? Well, notice here I'm 1 away. The next point over is 4 away. The next point after that, that's down a long ways. That's down 16. So what am I multiplying by each time? By 4. That tells me it's got to be a 4 to the x. But of course, it's not just 4 to the x, is it? This one's below the asymptote. Therefore, it's going to be a negative 4 to the x. And our asymptote was moved. Notice our asymptote is up at 6. Therefore, we have a plus 6 on the end of our equation. All right. Let's keep practicing that. Please write the equation for this graph. And one of the first things I hope you're doing as you look at this graph and try to figure out the equation is I hope you're mentally putting that asymptote in. Because figuring out where that asymptote goes makes writing the equation a whole lot easier. Because we can tell, here I'm down 1, 2, 4. I'm just counting from that asymptote. It makes counting a lot easier. So if I'm down 1, 2, 4, what am I multiplying by? 2. So I know it's going to be 2 to the x. It's down below the asymptote, therefore it's a negative 2 to the x. And where is our asymptote? Negative 3. So notice we got a minus 3 hanging on the end. We're going to do one more practice problem going this direction. So please now write the equation for this graph. And so once again, I hope you're starting by envisioning the asymptote in there. And then once we have the asymptote in, it's a matter of how high are we going each time. So this is up 1. Then we're up 3. Then we're up 9. So what are we multiplying by? 3. So that tells me it's got to be a y equals 3 to the x. This one's above the asymptote, so it's not negative this time. But it has all been shifted down, more specifically down 7, so it's 3 to the x minus 7. So now we're going back to the direction we're used to, but in this case, notice I'm not giving you the whole original equation. I'm giving you the parent function and the transformation. Because I want you to be able to operate from those individual pieces. So we know this is a 2 to the x, and the whole thing shifted down 4. That's the only transformation. Go ahead and make that graph. All right, so now making this graph, I hope the very first thing that you already thought to do was to draw on the asymptote. So since this one is shifted down 4, that does move the asymptote. The only thing that moves the asymptote is shifting it up or down. And then having done that, it's a matter of where's the first point go. Well, since there's no other changes, my first point's still going to start up 1. And then since it's 2 to the x, I'm going to be doubling that height as I go to the right. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and so on. That's going to the right. I'm multiplying it by the 2. As I go to the left then, I'm dividing by 2. So each of those gets smaller and closer to the asymptote. Then you've drawn enough points. Go ahead and draw the curve through. And make sure you have this graph correct. As a side note here, I didn't ask you to find the equation, but some of you instinctually did. It would be y equals 2 to the power of x minus 4, in case you're curious what that original equation would have been, or want to check yourself. All right, I want to practice that again here. So here I'm telling you the parent function is y equals 3 to the x, and there's 2 transformations in this case. It's shifted up 1 and reflected across the x-axis. Please make the graph. All right, so when making this graph then, again, the very first thing I hope you're doing is drawing in the asymptote. In this case, it's up 1, so draw in that asymptote. Then our first point, it's going to be 1 away. In this case, though, since it's reflected across the x-axis, that means it's going to be 1 down. Once we have that first point, then because it's a 3 to the x as our parent function, I'm going to be tripling that distance. So down 1 becomes down 3. Down 3 will become down 9, and so on. Now, of course, that's going to the right that I multiply by 3. As I go to the left, then, I'm dividing by 3. And then having put in at least 2 points on the fractional side, we can go ahead and draw on the curve, and you got what your graph looks like. And for those of you who, again, decided that you wanted to figure out what the original equation was, it'd be y equals 3 to the x, of course. The shifting up 1 has a plus 1 on the end. The reflection means it's a negative 3 to the x. So the equation was y equals negative 3 to the power of x plus 1. In case you found it just for fun. All right, now having practiced these, we're going to take one new little twist at these exponentials. We can also face problems that look like this. Y equals 1/2 to the power of x. So write this down as your next equation. Now when we have y equals 1/2 to the x, you notice that it's just a number raised to the power of x. So because of that, this is the parent function. It's still okay for it to be the parent function even with the number raised to the power of x is a fraction like this. And since our original equation is the parent function, that also means there's no transformations, which then means that our asymptote is still at 0. So we can know all that stuff right off the top. Now we go ahead and start looking to see what's the graph going to look like. Well, first of all, draw in the asymptote. The asymptote wasn't moved up or down at all, so it's still at 0. Use a heavy hand to make it clear that your asymptote is there at 0, because sometimes it can be hard to see it when it overlaps the x-axis like that. And then we need to put in our first point. Well, what's 1/2 to the power of 0? It's 1. Yep. Because everything to the power of 0 is 1. Even a fraction still works the same way. Anything to the power of 0 is 1. So far, it's exactly the same as any other that wasn't a fraction. But this is where things are going to start looking a little different. Because as I go to the right, if it's 2 to the x, I multiply my height by 2. When it was 3 to the x, I'd multiply my height by 3. If it's 1/2 to the x, I multiply my last height by 1/2. So 1 goes to 1/2. And then as I go to the right, that's going to get cut in half. And that gets cut in half. And that gets cut in half, and so on.
Oh, wow, that's cool.
Okay, what about going to the left? Well, when it was 2 to the x, we would divide by 2. When it was 3 to the x, we divided by 3. So here we're dividing by 1/2. But how do you divide by 1/2? It's 2. It's multiplying by 2, yes. Dividing by 1/2 is the same as multiplying by 2. So as we go to the left, then 1 is going to double to be 2. 2 will double to be 4, and so on. And so this hopefully feels very familiar. It's basically the same thing as 2 to the x, except it's been flipped around. Once you've drawn your points, go ahead and draw in your curve there. All right, now domain and range. Since this is an exponential, it has the same domain as every exponential, which is all real numbers, yeah. The range, of course, is talking about our y values. Our y values start at 0, and it's everything above. So it's y is greater than 0. And then one last little detail I want to give you that's going to touch on some of these kinds of things. This is the first graph that we've seen. Excuse me. It's an example of exponential decay. So exponential decay occurs anytime that we have a number that's smaller than 1 that's raised to the power of x, because it means that as we go to the right, as our x values get bigger, the amount that we have, which is our y value, gets smaller. All the graphs before this that we saw were examples of what we call exponential growth, because our y values were actually getting bigger as we went to the right instead.